Yeah, good morning, everyone. And today, my partner and I will give you a session about our work to implement pipeline processing language in OpenSearch with Apache Calcite. Okay, my name is Lantao, and he's my colleague Heng Qian. We are all from OpenSearch Shanghai team. Here is our agenda. First, I will give you a recap about OpenSearch query, and we will go through the high-level design and architecture of our query engine v3. And my colleague will give you the deep dive into the optimization and the new features. And last, we will give you the roadmap. Okay, let's begin with the recap of the OpenSearch query. As you know, OpenSearch provides a specific search language called query DSL. So DSL is flexible with the JSON-based interface. Here is an example for the DSL. And we also provide a SQL interface, which bridges the gap between the relational database conception and the Docker rental data. So you can use your SQL knowledge to query and analyze data from the OpenSearch. So here is also the SQL query, which is to group by code value. This SQL is equivalent to the previously DSL. And we also have a language we call the pipeline processing language, PPL. PPL is focused on processing the data in a sequence row and use the pepper mark to combine different commands together to find and retrieve data. It's very particularly well suited for the analyzing some observability data such as log, metric, and trace. Here is the same query for the PPL language, which is equivalent to the SQL and the DSL in the previously slides. Okay, let's give a simple comparison about the different query. The DSL is, as you know, is very powerful and faster because most of the DSL will leverage the Lucene capability. But DSL has a steep learning curve, and it's very hard to read and write by human. And there is no any user-defined functions. For functionally, there is a little bit poor. So SQL is used widely in industry and has a lot of SQL standard. And you can use your knowledge to switch different databases, even using in the OpenSearch. So it also provides a powerful data manipulation. But SQL has also some limitation because the SQL is standard. So it has some limitation in dealing with the complexity problems. Also, SQL is also focusing on the structured data. So PPL is similar to SQL, but it's very easy to use and easy to write. And it's focused on the observability data, such as logs. Also can using in the time series data analysis. And PPL also a long chain of different operators together to deal with the complexity data transformations. But PPL is very new to user and new to AI. This language also can be translation. So most of the PPL queries can be translated to, or particularly translated to DSL. So we provide a tool to help you to understand the internal DSL of a PPL. So you can use the explain command in PPL or the explain endpoint. So it will generate output the explain node, execution plan of the PPL. So there is a logic plan and a physical plan. In the physical plan internal, there is a DSL inside. So we can copy out and format it as JSON. So that's what the DSL. So this tool can help you to understand the difference of the PPL and the DSL. Also, PPL can translate it to SQL. So we also use this command, explain command with extend mode or extend parameter. Or you can add extend format equal extend in the endpoint. Then the PPL will be generate the SQL. So this example about the PPL command and the relative SQL is in the right side. So you can see there is a much difference because SQL has some standard, so it cannot provide this powerful to simplify the query. Okay, even we have a simple language such as PPL, but we still have lots of commands. So to some new hands to to learn the PPL is still have some challenges. So we provide AI assistants in the Discovery UI. So you can write some natural language, and the LM model, text to PPL model, will help you to translate your natural language to a PPL query. So whenever you want to use the SQL or PPL, the SQL plugin is required to install in the OpenSearch. So after the plugin was installed, and you can use the different use the two endpoints, SQL or PPL, to query by SQL or PPL. Here the example uses the curl command to query. Yeah. Okay. After the recap, let's go to the architecture of the engine V3. So why we call it V3? Because there is a V1 and V2. So the SQL plugin has several years, and it started from the NLP China ES SQL project. This project has been deployed years. And based on that, we developed the V2 engine to support the PPL and SQL. So we introduced the type system. We supported the semi-structured data and support push down and multiple data source. Even we have V2 engine, we still have many challenges. The first challenges is the implementation challenges because we want to add more and more complexity queries and new commands and functions. That's we made the first challenges, implemented all of them in in the V2 engine. The second is in the V2 engine we list the virtual optimization rules, and we don't have any some cost-based optimizer or any optimizer. And even we have 50,000 integration tests, but compared to a virtual database, the testing is still insufficient. So our new solution is integrate the Apache Calcite. The Apache Calcite is is a Java framework that along the SQL interface and advanced the optimization for any queries. So it supports standard SQL, and it provides query optimization. It also supports third-party data source. And internal, there is a relational algebra manipulation. So that's why it can be do some query rewrite or query optimization. Okay, I won't go to the detail of the Calcite. So if you have some interest about the Calcite, you can go to the website. With the Calcite integration, now we can resolve the challenges that we listed above. Firstly, the Calcite is very common used library, and it provides lots of complex expressions, and there is lots of built-in functions internal. And also, the coolest thing is the Calcite provide a cost-based optimizer, and also include lots of metrological rules, and it can use the cost and statistics to find out which is the best plan to execute. Yeah, Calcite is widely adopted in industry, so there were lots of tests for this library, so I think that was more luminous. Okay, here is the Calcite integration architecture. So the query plugin is the SQL plugin. We rename it the query plugin, and it's in the coordinator node. So whatever the DSL API or SQL API are all sent to the coordinator node. So in the query plugin, the SQL and the PPL all use different endpoint, and the statement will be passed into different parser. So SQL parser and the PPL parser will output a common query AST, abstract semantic tree. And this AST will be fed into the Calcite. And Calcite will help us to generate the logical plan and the physical plan and execute. If some query in the physical plan can be pushed down to DSL, we also send this DSL API to the transport server. So that's similar to the DSL. Okay, here is processing. Whatever PPL SQL, they will be using the untl 4 to analyze its lexis or its semantic, and to create a AST. Then using the AST to fill into the Calcite. So the Calcite will create a real node. A real node is a logical expression tree, which is used in the Calcite internal. And Calcite also do some cost-based optimization work and to create the physical plan. Currently, we use the internal physical plan. It's called immutable nodes. So immutable real is the immutable nodes API. If we have the execution physical plan, then if we found some query can be pushed down to a DSL API, we will push it to generate the OpenSearch DSL API. Okay, we will go through details for that. Since we have AST already in the V2, so we want to reuse that. So we didn't start from the SQL interface. We just use the AST. So we use the real builder. It is a tool in Calcite. This tool can help us to create a logical relational expression. That's the real node. So the real node has lots of definitions such as sort, join, project, filter, scan, etc. So the real builder finally will help us to build a tree as a logical plan. So we created a visitor to transfer the AST node and to create a real node. Here is example. In this function, this visitor relational function, the input is relation. Relation is AST, which express a table or some index or something else. And we use this function very, very simply. Use the real builder. We get the real builder from the context and invoke the scan API to create a real node. Then it will be returned. So in the visitor, there are lots of visitors. In the visitor mode, finally a tree will be constructed. Okay, that case give you a relation to scan interface, but how can we, mapping the schema? Because we use the real builder, we missed the the SQL layer. So the interest of the schema actually is the real OPT schema. Real OPT schema is listed in the optimizer layer. So the interface we are using the real OPT schema. The real OPT schema has an internal container we call the Calcite schema. And the Calcite schema will finally call the schema, public schema API. So we ingested the OpenSearch index schema into the public schema API, the schema API. Then will be called to the real OPT schema. So the relation in the left side using this pipeline will go to the table scan. We created a logical node called the logical index scan. So the schema is inside the logical scan. Even we have a schema mapping, we still need to mapping the different types because we have different systems. So in OpenSearch, each index has an index mapping. The index mapping, the picture listed some dynamic mapping types. For example, Boolean, float, double, etc. And even we have this, but this different with the Calcite type. So we introduce a bridge type system we call the XPR type. XPR actually is used in our V2, so we reuse it as an interface to mapping the index mapping and the Calcite type system. So XPR type provides two types. It's a call type and the OpenSearch data type. Call type is the one can easily to mapping to the database type, for example, integer, long, etc. But for the OpenSearch data type is for specific types in OpenSearch, for example, IP or point or something else, which is defined in OpenSearch only. So we use that interface to mapping them. Now we have the real data type is the interface internal the Calcite. So this picture listed how we mapping the different types. So we can from the request, OpenSearch request to the OpenSearch response. The OpenSearch request will query the OpenSearch index mapping. And this mapping will translate to the XPR type. So XPR as the interface layer. The XPR type will map each to the Calcite map in analysis stage. So in the analysis stage, after the analysis, we will build a logical plan. That's each plan there is a real data type system. So in the real data type, there also have two types. One is the basic SQL type, another is Java type. As you see, some primary types such as integer, long is using the basic SQL type, but for the user-defined type such as IP, address, or something point, something else will be using in the Java type. And whatever the SQL type and Java type, we use the Calcite internal execution as in memory, so it will all translate to the Java types. Its class. So we use the JDBC interface of Calcite to return the output. So the JDBC will return Java types, Java SQL types. And we finally mapping the Java type to the XPR type and fill the XPR type into the response. So that's the flow of the system type. Okay, here is an example of optimizer. My colleague Heng will give you more detail about how to push down logic plan or query plan to DSL. Here you can have a simple example. You can see there is many rules we created, and the original plan is the two-table join and aggregation, and from the left to the right, the query was simplified because there is a much push-down rule be addressed. So and push-down rule addressed, the query will be simplified. So at last, they only have to scan and a join operator. But even there is a simplified query, but it's still some operator cannot be pushed down. For example, the join. So we still need to provide a way to execution that operator. So in Calcite, we're using the internal immutable interface. So the immutable real interface translates a real node to a immutable operator. So the immutable operator, is meant to have interval in Java. So it can be execution row by row. So we provide some roles to create the specific operators to the physical operator. For example, we have immutable index scan roles. Okay, now we have a plan with simplify, and we have a plan with immutable operators. But we still have lots of expressions in the SQL. For example, there is a filter in this plan, and there is maybe a little small. It's a larger than b divided 10. This is a simple expression. The expression will construct an expression tree. So in Calcite, the expression tree will be translated to the link4j expression. With the link4j expression and the plan, the Calcite will help us to implement it to a statement, a block statement. The block statement API will be using Genano compiler to generate Java code. So the query like this will be finally constructed to Java code and to be compared in runtime to execution. Okay, another important thing is how to register the functions such as UDF in Calcite. Actually, Calcite has a lot of built-in functions, so we want to reuse them. Also, we still need to build in some specific UDF for OpenSearch specific usage. So we extended this, the plugin, and we created a PPL function table, which used to register functions. And here is an example how to write a UDF. So a UDF has 4 fundamental. It must extend the SQL user-defined function API. This is provided by the Calcite. And also need to provide a SQL return type reference, because there are lots of functions that have return type, maybe have different type. So we need to have some inference which type should be the better for this invoke. So another, we need to provide a type checker to make sure if a wrong type, if a wrong type can be stopped in the compiling stage and the analysis stage, not in runtime. So we also need to provide implementation details. So we combine them together to implement our UDF interface. So here's an example about a CRC32 function. This function, you just need to extend this interface, the call interface, implementer UDF, and to rewrite 2 methods. It's get return type info and the get the operator metadata method. So, and you need to also provide a static method in Java. So this is done, the UDF. And the framework we provided will help this function to adjust it to the Calcite internal. So you can use it in the query, the PPL query. Okay, let's go to more details. You can use this link, for example. Okay, let me forward the next part to Heng.
Okay. Hi, morning everyone. I'm Heng. I'm a software development engineer for AWS Shanghai. I'm currently working on the OpenSearch PPL. In the next section, I will introduce some work about the optimizations we've made on the V3 engine. The first part is about leveraging the Calcite optimizer to accelerate our PPL query. As mentioned above, Calcite has its advantage on its mature cost-based optimizer. The cost-based optimizer is a mechanism to find the correct execution plan for a given query with the lowest cost. And first of all, as we've talked about the cost of a plan, we must need a cost estimation mechanism. And it's usually based on the metadata, like the input rows count and the calculation logic of each operator. And we also need many heuristic optimization rules that help us continuously generate new plans. Then we can calculate the cost of them repeatedly and find the cheapest plan in the end. This iterative process is initialized with the original route plan and will not stop until no new plan will trigger any new rules. So after integrating with Calcite, it's nearly 300 plus rules have also been introduced into our PPL optimization process. It includes some most common used, but also very efficient optimization rules, like the predict, pushdown, column pruning, constant folding, join strategy, and etc. I introduced some of them and how they affect the cost of our plan in the following pages. The first one is about predict pushdown. Consider a scenario where I want to search our company's data to find employees who are very young yet highly paid. To find these talented guys, I quickly write a list PPL query without thinking too much. It's actually an efficient query if looking into its basic plan, as it needs to perform intersection join for all records from both sides. But thanks to the optimizer, it finds the filter right upon the join and split into two appropriate filters and push down the filters through the join to each side of its children. So these two filters will significantly reduce the input row count of the plan, of the join. So from the perspective of cost estimation mechanism, it computes the cost of a join by multiplying the left row count by the right row count and some other factors. As we've pushed down the filters through the join, the row count of these two sides are greatly reduced. So the cost of the optimized plan will be smaller than the basic plan. And the second one is about the column pruning. This PPL query has a join command and another states command of it. In its plan, you can find that each child of the join has to fetch all columns from the index. However, we actually don't need all of them. So the optimizer will find the exact columns we really need for this query and make column pruning for these two project operators. The cost of the project operator is calculated by multiplying its input row count by its expression size, since we've pruned the column size to 2 for each side. So the cost becomes smaller than before. Apart from those 300 optimization rules already existing in Calcite, the optimizer system also allows us to develop some customized optimization rules. This gives us more opportunity to enhance the performance for our customers' various scenarios and also address other performance challenges. This is the case of a query from ClickBench. This query aims to perform some aggregation on 19 kinds of expressions. We all know that aggregation is another very heavy operator, so too many aggregations will definitely bring a lot of overhead to our cluster. So we need to find a way to optimize it. Based on the mathematical property of the sum transformation in the bottom left, the original 19 aggregate functions can be reduced to just 2, including a sum on the field and a count. And the original 19 aggregate functions can be calculated by reusing the output of the least two aggregate functions. And let's see how it affects the cost of the plan. The cost of aggregate is calculated by multiplying the input row count plus the aggregate core size, another factor. Since we reduced the aggregate call size from 19 to 2, so the cost will also be reduced by 45 times. Apart from this kind of optimization rule, we also implemented many other rules to help improve the performance of PPL. They are almost about the push-down operators into our index scan operator. Let's explore them in the next part. The next part is about leveraging OpenSearch Query Builder to accelerate our PPL query. As we know, as a plugin of OpenSearch, our PPL can only be run in the coordinator node. It's actually a single node serial processing for a query. So this could be a significant limitation on the performance, especially when we have to fetch and handle a large amount of data. However, the search query in OpenSearch does include some parallel processing, both in its query phase and its fetch phase. So it can be a good idea to push down the PPL to be an OpenSearch query, just like DSL, to leverage its parallel processing. So this picture shows how we made it. Firstly, in the optimizing phase, we've implemented many related optimization rules to push down all basic operators into the push-down context we've defined in our index scan operator. They are actually constructed as many push-down actions within the context. And each action includes a digest of the operator itself and the Lambda function about how we build the OpenSearch builder. In the figure, you'll see that we can push down almost all operators like the project, filter, sort, aggregate, but not join. Because join is an operator that to perform intersection join across multiple indices, while our DSL didn't support this feature so far. And secondly, in the execution phase, we have built the push-down context into a search request based on the actions we've already pushed. And then we send the request via our node client to fetch all already processed data from the index. And so this is the process, shows how we push down the project operator into OpenSearch query. You'll find that we just need to put the projection fields within the source statement of DSL. And this one is about field pushdown. We push down the where command into the query statement of the OpenSearch DSL. Besides, we also need to choose the right corresponding type of the search query based on the functions query string here used in PPL, and put parameters on the right position. Actually, we've implemented a tool named Predict Analyzer to help us do such thing. And this is about sort pushdown. We use the sort statement to implement the sort command in PPL. Both queries support the sort direction and non-direction, so they can match perfectly. And with the sort pushdown optimization, we are also able to further enhance our join process. For join, we usually have two types of physical implementation. One is hash join, and another is sort mode join. But since we can always push down the sort operator into scan, then we would prefer to choose the sort mode join with both sort operators being pushed. And its time complexity will be m plus n. So it will be much faster than the block hash join we already have in the legacy engine. And last one is about aggregate pushdown. We use the aggregate statement in DSL to implement that in PPL. You find that the PPL is quite simpler than the equivalent DSL, even though I've omitted most part of the code in the DSL here. And although we are able to push down so many operators, the UDF in PPL will prevent them to be pushed down because DSL may don't have the related implementation for most of our UDF. But luckily, OpenSearch supports the script query and allows customized script engine for our plugins. So we ingest a new script engine customized for Calcite expression in our Circle plugin and construct the script query to further enhance our pushdown process. And this is the process of how we do the script pushdown. In the push-down process, if we cannot push down the operator and expressions by using the primitive DSL statement, we will let it fall back to the script pushdown. And different operators are required to generate their corresponding script context, but they can all share the same script language and the execution logic. So when the search request with the script is submitted, our pre-registered script engine will try to deserialize the script bytecode into its original Calcite expressions. It will then generate code for the expressions, compile the generated Java code, and execute the code to return the final results. And let's see what we can do with the script pushdown. This is the analysis query on OpenTelemetry log. It performs multi-layered processing to generate HTTP status statistics. This query workflow involves parsing HTTP status codes from the log body content and evaluating these codes across various operational scopes, and finally computing the statistical aggregations. Although the PPL is somehow complex, we can optimize this execution by pushing down the entire operation into a single aggregation DSL with embedded script. That's pretty cool. And after talking about optimizations, I also want to introduce the benchmark we've done comparing the performance of our V3 engine with the original V2 engine. And this is the benchmark performs on the big 5 workloads. It shows a 30% performance improvement. While this gain is positive, it's less dramatic than our expectation. It's because big 5 queries are typically straightforward and simple, so allowing even V2 optimizer can handle them effectively. So to better evaluate our V3 engine's capability, we introduced ClickBench. It is a more comprehensive and challenging benchmark shoot. The test results shows that V3 engine is 3 times faster than the V2, and that is a very impressive improvement. Apart from those performance optimizations, we also built lots of new features on our V3 engine. After we've migrated all existing commands and functions from V2 to V3, we also implemented many new useful commands like the subsearch, join, lookup, even states, and lots of new functions. And for subsearch, we've supported all 4 kinds of subsearch, like the in subsearch, existing subsearch, Scala subsearch, and the relation subsearch. And for join, we support all common use join type and some extended features like the override and the max match rows. We also support the lookup command. It can enrich your search data by adding or replacing the data from a lookup index. And the states command to enrich your event data with calculated summary statistics. Besides those new commands, we also added many new functions like the JSON-related functions, collection-related functions, and more aggregated functions, and the window functions for the new added comments, event states. We want to introduce the functional details about these new features in this session. If you are interested in them, you can refer to this link for more information. And we also recommend to attend the session about using PPL on the OpenTelemetry analyzation. It will be held in the Gold Room later. That's a presentation from me. Let's hand it back to Lantao. He will introduce our future work roadmap.
Okay. Okay. For the roadmap, what's the next stage we want to introduce is continue the command function in PPL. And also we are providing further optimization rules. This is our push-down rules and capability. Another thing we want to think in and we want to provide is a pluggable execution backend. For much, currently we still use some memory execution, so we want to have different execution backend. And we also found a lot of comments about the schema-less test. So currently with the Calcite strong schema system, we want to provide the option for the schematic support. Okay, some command has already merged internally, and some is still working in progress. This is the list of the roles we are working on in progress. Okay. The last lecture I will give you some detail about the evaluation of our engine. At the beginning, the next engine V1 and V2 is using the iterator model. We call it the canopy database. And we are not here. We are not here in the Calcite integration. We use the codegen. The codegen means we compare a query to a Java code, and rather than interpreting, so it's much faster than comparing the mechanical model. Later this year, we will try to integrate the pluggable vectorized execution backend. So yesterday, I think Mike and Mark is already have a session about the data building. So tomorrow, I think there is another session. We will give some insight about the DevOps. Okay, I think that's all. Thank you, everyone.